Okay, guys, welcome and good morning to everyone. Good afternoon, depends again where you are. And today we have the pleasure of having Andrew Koc, and he's going to speak about the end of time evolution in self-interacting vector theories. Andrew, you have 1 hour. Time is pretty flexible, and if you want, question can be at the end or during the talk, as you prefer. So you have the stage, and thank you so much for being here.
Yeah, thanks for the invitation. I'm happy to have anyone interrupt if they have questions. I've also left quite a generous time for questions at the end. So we'll see how we get on. This is based on some work I've been doing quite recently with Fetty Ramos and Null in Koc University. And a couple of other people to mention. So there's been quite a flurry of activity on this kind of thing. So the main things I'm addressing here are this recent PRL with Fetty. There's this Katie Clough and a couple of other people paper, this Moon Zhang paper. These are all on the same kind of topic. And I'll talk a little bit about our latest preprint. And I should also mention that most of these works have missed these earlier contributions from Esposito Ferreza from 2009. Yeah. Okay, so what I'm actually going to talk about. So the idea is to just review well and ill-posedness for anyone in the audience who isn't already familiar. Talk about what goes wrong with nonlinear Proctor theories. Maybe do a couple of easy examples beforehand. We'll see on the way to this problem that the problem is due to the constrained nature of the fields, and maybe what that hints about some other theories that might have the same problem. So in the literature, there are 2 issues that have been proposed for the breakdown time evolution in nonlinear Proctor theories, and I'll also explain why the second one of those things is just a technical challenge and not actually a breakdown of time evolution in the true sense. And then I'll talk about, kind of what we're doing now. And maybe I'll mention a few of those as we go, if it's relevant. So what is well-posedness? First, you've got to decide what type of problem you're talking about to ask whether it's well-posed. So well-posedness of the Cauchy problem, that is the initial data value problem, which is basically if we have some differential equations and some initial data, or we are going to be supplied with arbitrary initial data, the question is, can we get a unique solution? And does it depend sufficiently smoothly, in some sense, on the initial data, the solution, right? So that's the basic definition of well-posedness for the Cauchy problem. And the answer is not always, right? It depends on the equation. So for instance, if you have a Laplace type equation like this, and you try to solve it as an initial value problem, right? So I give it some initial data like this, you'll see that this thing diverges no matter how small I make this initial velocity. I mean, as I make the initial velocity smaller and smaller, this thing diverges exponentially, even though the amplitude of this velocity is getting smaller and smaller. And I could have any positive power s, because this is an exponential divergence. And so if you try to solve the Laplace equation as an initial value problem, you won't get this continuous dependence on initial data, so it's not well posed. You can see this is a problem for physics, right? If I have some experiment and I set it up, I can only know my setup to some finite accuracy. And so if an arbitrarily small difference from what I think the setup is can cause a exponentially large change immediately, then we're not going to be able to do any experiments, right? So this is kind of not good for physics. The one thing that you have to remember, though, which is not obvious at all when you first look at this, is that this well-posedness actually depends on the formulation of your theory or your equation. So for a given set of equations, you can see how they're well-posed, but if you have some physical theory, you can have a bad formulation which is ill-posed and a good formulation that is well-posed. So you've got to be quite careful about whether you're really finding ill-posedness of the theory or just the specific set of equations you set up to try to solve. So more generally than that simple Laplace equation, we're going to have some equations which look like this, where we have some function of the space-time coordinates, all of the fields u and their first and second derivatives. I'm not going to consider higher derivatives in a second. And figuring out whether this is a well-posed equation in general is really, really difficult. It's basically a whole field of mathematics that's still ongoing. But for our purposes, we can just use some necessary condition, which is for 3 to be well-posed, the linearized frozen coefficient equations must also be well-posed. And this will get us to something very simple to compute and which will give us everything we need in this case. So first we linearize, right? We just expand this equation around some arbitrary solution, which I'll call u0. And then we'll have an equation like this. So the next part is, the next simplifying step is to localize the equation. This is also remains a necessary condition if we do this. So basically all of these coefficients just come from differentiating and evaluating on the background solution. We treat them almost as if they're constant, or you can imagine zooming in on a local patch and doing a Fourier transform of the fields, this kind of thing. So because this is a high frequency problem, right, if we go back here, the problem here is exactly because the frequency of this thing is diverging in the epsilon to 0 limit. Is exactly what leads to this problem. So if we do so, we can just replace all the derivatives by some one form psi and expand around large components or large spatial magnitudes or something like this, and end up at an equation of this form, right? So this is just the term highest order in derivatives, but with the derivatives replaced with this one form psi. And this is called the principal part of the equation, and it allows us to define this principal symbol, which looks like this. So it is just the linear operator acting on the perturbation in this equation. So the necessary condition, not sufficient, but necessary condition for the full equations to be well posed is that if you solve this equation, that the determinant of this principal symbol is 0 for the frequencies psi 0, you must only get finite, i.e. bounded from above growth rates, right? So you can have some imaginary frequencies, but there should be a maximum imaginary frequency. And if you don't have that, then you have ill-posedness. If you do have it, you don't necessarily have well-posedness, but if you don't have it, you definitely have ill-posedness. Okay. So the simplest example I can think of, which is relevant, is this scalar field example, right, where we have some potential for the scalar field and just the standard kinetic term. And if you apply this analysis, you will find out that the condition is that the metric signature must be Lorentzian, as in minus plus 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 or plus minus minus minus. Otherwise, it's ill-posed. And in particular, the metric has to be Lorentzian everywhere on the space-time. So the question is why? So the easiest thing to directly see is that if you have Riemannian signature, or plus or all minus, you need a boundary condition to the future, right? If you're trying to solve a Poisson equation, you generally want to put a boundary condition all the way around to get a nice solution. And that means we want to put a boundary condition in the future of the time we're trying to predict. So we need to know the future of the thing that we want to predict, which is not very good physics. Or in terms of this well-posedness analysis, using this necessary condition, the principal symbol is just these wave vectors contracted with the inverse metric. And so at least in the right coordinates in the local patch, this means that the frequency, if we have Riemannian signature, will be purely imaginary and unbounded from above, right? Because we can make the wave number larger and larger, and so the growth rate will increase and increase. And that's why you can't have a Riemannian signature and a well-posted initial value problem for a scalar field. And so in 4 dimensions, there's only 3 options, right? You either have a Lorentzian signature, Riemannian signature, or 2 minuses and 2 pluses. And the problem here is you'll always have closed time-like curves, right? If I have 2 dimensions with the same signature, I can draw a circle. So closed time-like curves will stop me being able to evolve in time. So the next step towards nonlinear Proctor theory is to look at first massless and then massive vector fields. So we have this action, right? The first term is just that of electromagnetism, standard kinetic term for the vector field in some sense, and then a mass term. And when the mass is 0, our equation just looks like this, and we pick the Lorentz gauge, and we again just have this wave operator acting on x as the principal part, and so it has the same well-posedness properties as 4 copies of a scalar field. Apart from, there's one subtlety, which is why can we use the Lorentz gauge, right? So the condition for the Lorentz gauge is just this, and let's assume it's not satisfied. Can we get to a gauge where it is satisfied, right? So this is the U1 gauge transformation for electromagnetism, and what we want is for this new x to have to obey the Lorentz gauge condition, and in terms of this gauge parameter, it's just a wave equation, the scalar wave equation. We know it's well posed. This has a unique solution with smooth dependence on initial data, so that's why we can use the Lorentz gauge, and it doesn't change any of the analysis, and we just have 4 copies of the scalar wave equation in terms of well-posedness. So what about massive vectors? Well, this is very similar, apart from we have mass term on the side of the equation, and instead of the Lorentz gauge, we now have the Lorentz condition, which is exactly the same. This divergence has to be 0, but it's now a necessary condition and not a gauge choice, because if we take this divergence, take a divergence of equation 10 here, well, this left-hand side, this double divergence of f will vanish, and we'll just have the mass times this divergence is equal to 0, and for non-zero mass, that means the divergence is 0. Right. So what about the thing I'm actually here to talk about, self-interacting vectors? So this can, very similar steps appear for an arbitrary potential depending on x squared, but I'm just going to look at the quartic one here for to be kind of explicit. So the new term is just this one, right? We have some quartic interaction where we have x to the 4 in some sense. And what's going to cause us the problem is exactly when we take this divergence of equation now 15, this is no longer the Lorentz condition, so it doesn't resemble the Lorentz gauge anymore. And so what's going to happen is that we're not going to have a simple wave equation, and the thing that you get will have some problems. So let's have a look at what the principal part is, because it's more complicated. So we just use this generalized Lorentz condition. We're going to call these generalized Lorentz conditions the thing you get by taking the divergence of 15. So we're going to use that to substitute out this divergence of x, and we'll end up, after a little bit of fiddling around, with a principal part which looks like these 2 lines. So this z thing is just the derivative of the potential with respect to x squared up to some constant scalings, and z prime is its second derivative. Yeah, and so we have something that looks like the wave operator on some effective metric, some different metric, which we call g bar, which is just zg plus 2z prime xx, right? this thing looks like an effective metric, but then there's this leftover piece. It actually vanishes in 1+1 dimensions, kind of surprisingly, but generally it does not. However, it doesn't affect the principal, the characteristic frequencies kind of at all. So if we just extract the principal symbol from this, it gets expression, and taking the determinant, instead of getting n copies of this dispersion relationship that you get for the regular vector field, you get n-1, and you get 1 degree of freedom, basically, that that is governed by this effective metric instead, right? So we have n-1 degrees of freedom, which just follow the null geodesics of the spacetime metric in the high frequency short scale limit, and 1 which follows the geodesics of this other metric. And this is going to cause us a couple of problems. So in particular, even if the background spacetime metric is perfectly okay, this effective metric, which is in red, can have the wrong signature, it can have singularities, it could have all kinds of problems. So in particular, it will be singular when the determinant vanishes. And again, you can just calculate this directly, and you'll find, okay, it equals, it's proportional to the spacetime metric, but then it has these two factors, both of which are not positive definite or negative definite. They're not sign definite, but yeah. And if you just look at them, right, if we start near x equals 0 or x squared equals 0, then this one will always be encountered before this one. And so if you're thinking about some small amplitude fields that grow, something like that, then the main condition for this thing becoming singular is just x squared is minus lambda over 3. And in particular, it becomes singular at finite values of the vector field. And this is not a coordinate effect, which you can check directly by calculating the curvature scalars of G bar, and they do diverge. So in particular, right, the kind of problem we have found is it's the same problem with trying to evolve electromagnetism on a background with a naked singularity. Right? It's this kind of problem, which I think is enough to say it's ill-posed. So the question is, does this happen? Right? If we start with the Lorentzian G, do we ever get to the singular point? And the answer is yes, it can happen for any value of m and lambda. So you'll see here. So blue is early times, purple is late times. You can see this G bar is evolving towards 0. And this is for positive m squared and positive lambda. So positive m squared and negative lambda. Again, we see actually we cross 0 in simulations quite simply. I'll talk about this thing and why there appears to be some kind of limiting process later. And then, so the other two signs, so if m squared is negative and lambda is positive, again, we get something similar where we approach 0 with, perfectly fine looking data. And on the right-hand side, we have both coefficients negative. And again, we cross G bar equals 0 very simply. And also, we've got an ongoing piece of work showing that you can actually achieve this kind of breakdown where G bar crosses 0 with arbitrarily little energy. So you don't need to put a lot of energy into the vector field. In certain setups, it can happen with, like I said, arbitrarily little energy. It's not a high energy phenomenon. High frequency, but not necessarily high energy. So what is this this other problem? So this arises in the 3+1 decomposition most readily. Also in Hamiltonian analysis is how the other group found it as well. So in the 3+1 decomposition, right, we decompose the space-time metric using this lapse, shift, and 3 metric. And the vector field we decompose as some electric potential times the unit normal to the 3 surfaces, and some vector potential which is orthogonal to the unit normal, or lives in the 3-dimensional spaces. So what's this new thing? So if we look at the evolution of the electric potential phi, you'll find this 1 over g bar nn in 2 places, and they don't cancel out generically. And so there's going to be problems when this hits 0. The other thing is there's this separate constraint equation, which is, you can think that's like the 0th equation of, like in terms of the vector equation, it's the 0th, which is, well, so in the quartic potential, this is a cubic in phi, and yeah, I don't know what to see. So what is this GNN thing? Well, it's just n, 2 copies of n contracted with the effective metric instead of the regular metric. So with the regular metric, it's -1, but with the effective metric, you get this expression. And so you can see it going through 0 is causing a problem, as saying that the 3+1 decomposition requires a unit normal that's time-like according to both metrics. Right, that's kind of the geometric way to see it. And it's worth noting that for lambda greater than 0, this term is the thing that goes to 0 when g bar goes to 0, and this is positive definite. So this is always, GNN is always greater than or equal to this determinant. And so if we go back here, for the lambda positive ones, the reason we can't evolve past 0, but only sort of try to approach it, is because we're getting close to g bar nn going to 0, and that will just break our numerics because we're using this 3+1 decomposition. Okay. So clearly it leads to some kind of singularity, and in terms of the Hamiltonian analysis, you can actually find out that it corresponds to a change in number of solutions to the constraint equations. But it's purely a formulation problem, right? What is the condition? GNN equals 0. What is n? N is the unit normal to an arbitrary foliation we picked, right? So clearly, if we pick a different foliation, we can have this happen at a different point, or maybe not at all. Okay. So the idea is, let's pick a simple example to just show that this is a formulation problem that can in principle be completely removed. So let's evolve this vector field on a black hole background in tortoise coordinates. If you do that, GNN will be 0 on the horizon, and so it will always blow up as in, the limit that tortoise coordinate goes to -infinity. But in horizon penetrating coordinates, the wave goes straight through and doesn't blow up. So on the left, we have the tortoise coordinates. Blue is the initial time, red is the final time before the code crashed. And you can see that GNN is approaching 0. This is GNN +1, and it's approaching 1. As we move further and further into the negatives in the tortoise coordinate, right? The horizon is at -infinity in the tortoise coordinate. Whereas these are actually Koc coordinates. They're a type of horizon penetrating coordinate. Don't use Kruskal coordinates because you'll have exactly the same problem, but at positive infinity to -infinity. And you can see here, hopefully, that the wave has a finite amplitude at the horizon, which is this dotted line, and nothing has blown up. In fact, GNN is trending towards -1 in general, everywhere, with just some oscillations.
Andrew,
Yeah.
can I ask you a question?
Yes.
Okay, so this is for my own clarification because I got
Mhm.
confused with two things. So when you presented the effective metric and
Yeah.
you said, look, this determinant of the effective metric can become zero. And this is a real singularity in the sense of curvature invariance diverging. That's what I understood at that
Yeah.
point. Right.
Yes.
So now you are dealing with essentially the temporal component, and
Yes.
you have that this condition is zero, and you're telling us that in this case, well, I mean, it can be a formulation problem, and if you have, just the wrong coordinates, you cannot evolve through. But if you have appropriate coordinates, you can evolve through. But
Yes.
this case, wouldn't this lead to the determinant being zero? This condition here.
Okay, so that depends on lambda, right? So with lambda negative, there's no problem with the determinant at all. So this is the determinant -1. You can see it actually starts quite large, but it never approaches -1. Right.
Right. So you're saying that it doesn't. Okay. So this is purely.
You can also see it here.
Yeah. So this temporal component being zero, it doesn't imply that the determinant actually vanishes, and therefore it's just a formulation problem. That's what you're saying.
Yeah.
Okay. Thank you.
Yeah. Generally, you need some off-diagonal components to compensate or something like this.
Right. So this would be simply like, Eddington-Finkelstein coordinates in Schwarzschild or something of the sort. That's what you're saying.
Yeah. But this is the RT plane in Schwarzschild, and these are Koc coordinates is the name.
Right.
They're very similar to crystal Schickers. They're just better at are going to infinity.
Yeah. Yeah, but is this generic? In some cases, actually, wouldn't these two things coincide?
Yes, so sometimes they coincide. So exactly, for instance, when if you have a solution where the spatial components is 0 for the vector, then they will coincide.
Right. So the case you were showing us was for a particular sign of lambda, right? So
yes. Yeah, I think it will be lambda negative, I think.
Okay.
Yeah. Yes, it is generally a formulation problem, but sometimes it could coincide with the real problem. Yeah.
But your point is that the real problem here is that the determinant vanishes.
Yeah.
Okay, and the G and N equal to 0 is just a bit naive, and it could be that it's not the real problem.
Yeah.
Okay.
Exactly.
Okay. Thank you.
Yeah, so I've actually got through this a lot faster than I expected. So just to talk about what we're doing at the moment, and maybe I'll blabber on about it for a little bit. So yes, the first thing, well, one of the things we have a student working on is looking at some further generalizations of Proctor, right? This is a very, very simple, perhaps the simplest step beyond Proctor is to add a self-interaction, but there are all of these various classes of beyond Proctor theories, generalized Proctor, extended Proctor, beyond generalized Proctor. There's a lot of adjectives Proctor, right? These things. So how much of this applies to them? Can they be saved by the derivative terms or the okay, and then there's another thing which I'll leave for a second. So because of the origin of this problem being the divergence of the kinetic part of the equations vanishing, anything with a similar structure is likely to have similar problems. So p-form fields generically, not just one-form fields, but 2 and 3-form fields should also have a similar structure and therefore likely a similar problem.
Andrew?
Yes.
So I guess that there's plenty of time for discussion. I guess we could kind of, I could ask you a question already at this point, maybe. Right. So, but related to precisely this point that you are emphasizing now, Well, as you well know, I mean, this sort of a loss of hyperbolicity issue was already known in other theories, and it appears in other models with, for instance, not only nonlinear self-interactions, but nonlinear kinetic terms like k-essence. Even, I believe, well, if you remove your mass term in your Broca and you have nonlinear electrodynamics, again, an effective metric appears and you can have similar issues. So the question here is what's specific to the Broca case, if anything, and what's special about it? Or is it just another case within a very generic set of models which has effective field theories breakdown because of some sort of, the dynamics being ruled by an effective metric that can have bad properties? So is there anything specific to the Broca case? Or it just falls into the generic class of problematic theories?
So there's a few parts to that. So the first thing is, I think it is a little bit surprising that just having a potential for a vector field is bad enough. I think this is already a little bit surprising. I mean, normally, right, people generally, I think, use scalar fields as guides for their intuition for what should happen. And adding a potential, I don't think people expect cause these problems, but it does. The other thing is, we relate to this effective field theory idea and also k-essence. So I should mention that Enrico Barause and a couple of his postdocs, or a postdoc and one of his students, wrote a comment to our paper pointing out that actually in the Stuckelberg picture, this problem is exactly the same problem as in k-essence. So they are extremely closely linked. Mm-hmm. As for this effective field theory view, that depends a bit on your perspective, right? Because if we're coming at this from a gravity perspective and we're thinking this is going to be embedded in some gravity theory, I don't think there are many people expect that gravity will be completed as a quantum field theory, and only one of these four options can actually be UV completed. I think it's this one. Mm-hmm. So there are, you could make some ad hoc changes like this fixing the equation approach to the other cases, but it's not even clear what this physically means if they're not UV completed. So those are the kind of the general comments I have on those kind of topics, I suppose. Yeah. Well, I think you're right in the sense that, it seems pretty simple to add self-interactions to the Broca field. And it's somehow surprising that it's not self-consistent as an effective field theory. I think I completely agree with you on that. Perhaps we were a bit too naive, just thinking in parallelism with the scalar field case. Yeah. And we need to work a bit more in this case, in the Broca field case, in order to get something that just as an effective field theory, it's consistent. Because of course, any high energy physics theorist will tell you, if you just present a Broca model with a mass term and without having a symmetry breaking mechanism to generate the mass, well, this theory is bad as a UV theory. I mean, it's unrenormalizable, whatever. So unless you do things to it. But as a classical field theory, as an effective description, it's self-consistent. You can evolve things, and that's fine. And the surprising thing is that here you just put your a to the 4 term, say, and it breaks down. You cannot simply evolve it. I definitely agree with you. But let me just point out that we are sometimes a bit too naive in our beliefs because we are guided by simple parallelisms. And and in this business of the Broca fields and the scalar fields, and this is different, but it was something that was surprising as well some time ago. So you have, as you know, these lumps of these bosonic fields, which are the bosonic stars, and you can have them in spherical symmetry, and that's fine. And you can have them rotating, but in the scalar case, if they are rotating without any self-interactions, they are simply not stable. And again, people were thinking, well, but that's something fairly simple, and you should just be able to get rotating solutions like you get in fluids, whatever, that are stable, but you cannot. So sometimes I think, these subtle problems emerge from some naivety in our
initial guesses. But I definitely agree with you that it was somewhat of a surprise, and I think that the question is how we cure it, but we'll get to that towards the end of your comments, I believe. So thank you. Well, that's
Yes, exactly. Yes. So the next thing I wanted to mention is that, you know, we've just been doing this on fixed backgrounds, and that's actually fine for the criterion for the ill-posedness. But the question is, when you turn back reaction back on, does the evolution just avoid this somehow? Right. I don't expect it will, but it could in principle. Yeah. So in previous papers, which kind of led us down this route, we found, you know, we kind of killed Fetti's vectorization theory, which he was a little bit sad about at the time. But so there's a question of whether these things, you know, whether you can avoid having ill-posedness if you have some tachyonic growth of a vector field. You know, is there any kind of vectorization that's possible? Like of spontaneous vectorization, I mean, of course. I mean, non-spontaneous is, you can probably do quite simply, I would guess. And yes, and then the final comment is, you know, can you resolve this by treating it as an effective field theory? And yeah, so the main comment is, if you want to UV complete this as a quantum field theory, you can look at S-matrix amplitudes and find that only this one can be done. All of the rest, if you try to UV complete them, you will end up with something that is not UV complete. So only in this case can something else from that point of view work. And there we're investigating, you know, if we fix the equations and we compare it to the UV completion and some other things, how does it perform? Is this actually just a signal that the effective field theory is breaking down? One thing to note actually is the condition for the EFT to converge, at least naively, is actually that this should be non-zero, not this one. So this breakdown happens before the effective field theory is completely broken, but it's still quite close. So it might just be that the higher order terms are necessary. This is an interesting thing. And the other thing for the other signs, right, the other three cases, is if we are interested in this as a gravity theory, does this S-matrix thing truly matter if, you know, we don't expect quantum gravity to be a quantum field theory? So those are kind of my last few thoughts. Yeah, and I'll open it to general questions.
Great. Thank you so much, Andrew. So now we have plenty of time for questions. So guys, please mute yourself or raise your hand and feel free to ask anything you want to Andrew. So I see Nuno, there book himself first, then Carlos. So Nuno, please go on.
Hi, can you hear me?
Yeah.
Okay, so my connection is a bit unstable here, so I hope it doesn't crash. So thank you for your talk, Andrew. It was very interesting. I have a question about something you said in the conclusions. So you got rid of this coordinate singularity by using a specific coordinate system, right? But you chose that coordinate system in advance.
Yeah.
Right. So, but well, in a generic time evolution, you don't know in advance if you are going to find such coordinate singularities, right?
Yeah.
So do you know how we could avoid this problem here?
Yeah. So this is another issue we're working on, and it's actually a little bit subtle, but you need to do something adaptive, of course, right? So the thing you want is that when this is getting small, then the spatial parts of the vector are also getting small. How exactly to do that without causing other problems is a different question, and we haven't fully solved that, but we're working on it. That's the main thing. Is this term is what makes it break down before it has to break down.
Okay.
Yeah.
So in principle, it is possible to avoid this, right? In a generic time evolution. That's your guess?
Well, not necessarily to avoid it, but at least to push it back until the foliation independent breakdown happens. Yeah, I would expect so. But yeah, I don't know. Maybe trying to minimize this contribution will cause some other problems that can't be avoided, but I doubt it.
Okay. Okay. Thank you.
You're welcome.
Thank you, Nuno. I see that Carlos has also his hand raised. Please, Carlos.
Right. So, Andrew, again, thank you for your talk, which I thought was very nice. The subject is very interesting. And you probably are aware about this work by Aoki and Minaitsuchi, where they are proposing some resolution of these pathologies of the
This was in the Procastars, right?
Yeah, so right. So they didn't look at time evolution. They make some comments about that, but they are looking at the elliptic problem. So actually this comes in the sequence, and I'm especially interested about this because we were looking at these sort of models. We construct a lot of solutions here, and we were at some point looking at the construction of Procastars, and then Masato actually started doing with self-interactions, and he observed at the point that typically you have a space of solutions where you have a domain of existence, which is typically some spiral, but in this case, it kind of just stopped somewhere. So the construction of the solutions just stopped. You could not, get something, your solver to kind of converge, and then you can identify a problem which is related to the divergence of some ARR component of these equations. And in this paper, they are calling this a gradient instability. So they are, calling that the equations, even in the elliptic problem here, they have this gradient instability. Right. So first of all, I would like to know how your comment about the relation of this with the issue here on the time evolution and hyperbolicity that you are discussing, if any. And then they construct some sort of UV completion, which is a scalar, well, it could be a scalar vector theory in which you could have some potential, and it has a kind of Higgs potential, and if you expand around the Higgs, there is one particular kind of degree of freedom that indeed then would become, as an effective field theory, the one you are trying to solve to start with, that is the self-interacting Proca. So, and it only works for the parameters that you've said, by the way, m squared positive and lambda negative, so it kind of matches well what you're saying. So, I mean, I would like to know your opinion about this. Is this the way to go, in your opinion? And the first part of my question is about this connection between this divergence, this gradient instability and this hyperbolicity issues. Is there a relation in your opinion?
Well, so if we just go back to one of my first few slides, when you have the Riemannian signature, this is exactly a gradient instability for the high energy modes, right? And the what makes it just ill-posedness rather than gradient instability that you could deal with is that the growth rate's unbounded. So the slight subtlety, I suppose, is that before getting to the gradient instability, we actually hit a curvature singularity, right? And that's where they don't quite match. So, I mean, if you look here in this regime where we're still evolving, even though the solutions aren't really meaningful, there will be a gradient instability in this region with unbounded growth rates, but it, I've already just jumped over a singularity unknowingly in doing the numerical computation. Yeah, so I mean, you can see that. So this is these are the convergence plots for just one of the variables in some particular point, but all of them look very similar, which is everything is converging basically exactly perfectly, then you get very close to the end, just after G hits 0, and all of a sudden the convergence picture flips upside down, right? And the higher resolution run breaks down first because this is a high frequency problem, so it's more sensitive to it. This is exactly what you expect from this like kind of graded instability picture of ill-posedness. Yeah. The other part was whether to use this, right?
Yeah, sort of model, yes, and then you expand. Yeah.
Yes, exactly. Yeah, and you end up with exactly
as
this.
you prepare, exactly. Yeah.
Yeah, so I mean, I think that's a very good option for those particular parameters. One thing, the problem is, this problem, as you mentioned, is a lot more generic than just this particular model. It's a nice example because we know a UV completion. So the real question is what to do about it when we don't know the UV completion. Right, that's the hard question. And you know, there are some options. You can do this. You can do a gradient expansion for the solutions, and actually, you never run into any of these. You never get the Skrotsky ghosts you'd expect from an effective field theory. You can, but this is, you know, it's an iterative thing. So if you want to do numerical relativity, at every single order, you have to solve something more complicated than the Einstein equations. And if you want to go to high order, this is untenable, right? So, you know, there's this other approach that, well, it's originally by Israel Stewart, but Louis Lerner and his collaborators have been pushing a lot, this fixing the equation approach, where you take the thing that's causing you problems and you introduce a new field, which just solves a dissipative equation where it tries to relax to that thing that's causing the problems, and you try to solve these equations. This looked quite promising in a lot of cases, but I don't think we have a very good handle on when it works and when it doesn't. And that's the thing we're investigating, which you can only investigate at the moment because I don't think anyone's got a good theory, like mathematical theory of these things, in specific examples where you do know the UV completion and you can compare. Yeah, we have some results on that, but they're not quite ready to share. It's not always obvious whether they're going to work or not, is my view, but yeah.
Yeah, well, perhaps we should be happy that we have some UV completions, and perhaps it's true that not all theories admit a good, formulation for sufficiently high frequencies. Perhaps it's too ambitious that think that any theory would admit such. You see, even in general relativity, we know it doesn't really work very well for very high frequencies. It's just that there the theory can survive because it hides its own problems behind horizons often. So this is not the case here. But if I mean about the parameters and the choice of them, the m squared greater than 0 and the lambda smaller than 0, of course, even a scalar field theory, if you choose the wrong parameters, it would just be pathological. I mean, if you choose a tachyonic mass, the theory doesn't work well. I mean, it's really unstable. And if you choose a potential that's unbounded from below, then of course, I mean, the theory again has the same sort of problems. It's unstable. So not everything has to work. I think that's what I'm trying to say. And it's great that some examples we can find something that, you know, you have something that you thought naively it would work, it doesn't, but you find a way out. So anyway, so I think this is a very interesting discussion, and let's see. Yeah.
Yeah, the only comment I'd add to that is that although the wrong choice of parameters in the scalar field is sort of bad physics, at least the math still works, right? You can evolve a unstable scalar field in principle forever. It's just, I mean, there will be hardware limitations, but
that's very true. At least, well, it makes sense. But if you put the self-interactions to be nonlinear, sorry, the kinetic term to be nonlinear, then
yes, then you run into exactly the same problem
yes,
because of exactly this.
Exactly.
But the Goldstone mode is the essence.
Yeah, so I think this has the potential to become a kind of textbook example of something that seems nice and it's not, and it's simple enough. But on the other hand, this sort of UV completion that you have in this slide, it might just, well, unless some pathologies are still found in the near future or far future, which I'm not sure, but it has the potential to show, because I was in the committee of Guillermo Lara, PhD committee, and this was a student with Enrico, and I learned about his UV completion of the KSs, and I was really surprised. I didn't know about it. I then understood that it was something that was known earlier, but you tend to think about the UV completion as something much more powerful and some much more complicated than the original theory. But actually, in that case, it was just a complex scalar field theory with a master that was the UV completion of the KSs. And I thought, well, this is even simpler, somehow. So yeah, I think these are very nice, working examples and proofs of concept. But as you say, I mean, with generality, we are not learning much yet. But my point was, these simple examples are somehow, very, very pedagogical. Let's see if they can lead us somewhere.
Yes. That's definitely the hope. Yeah.
So guys, we have someone else that wants to ask a question. Well, I have a curiosity. So you were mentioning that some of this game kills some of the vectorized the theories that predicts vectorization that Fetty has studied a couple of years ago, right?
Well, not this specific analysis, but I imagine something similar would be found if we went back and did it. Yeah.
Yeah. So my question is because I was working at the same time as Fetty on vectorization, but I was working on a slightly different perspective. So because he was having a kind of Einstein frame vectorization, prescribing some potential precisely that has some coupling, while I was working on the Jordan frame. So basically, I have a photon, and then I have just a term that is Ricci or Riemann times x mu, something like R nu x mu x nu. So in that case, that would be a kind of mass term that gets dynamical only when the space-time is quite curved. So my question would be, when you study scalar field, it's easy to do something in the Einstein frame and then say the Jordan frame should be equivalent. But for vector fields, it's not that trivial. And I think Fetty had also a paper about this. So is this completely equivalent in a Jordan frame? Would you expect something like this happening when you have no minimal couplings as with vector and curvature?
Well, so the main thing is that the Jordan frame version of Fetty's thing looks nothing like what you were describing, right? It's got all kinds of awful terms in it. But I think that the same thing sort of has to happen. And the problem can also be described in terms of an effective metric going singular, in fact. And it's basically a vanishing of this. This just becomes trivial at some point, and it looks non-perturbative in the analysis we did. I imagine it'll lead to some ill-posedness if we repeated this kind of analysis. And so the problem is basically if you have a dynamical mass term, that if you have it positive in some region and negative in some region and continuous, it's going to be zero at some point. And that generally leads to the vanishing of this equation and bad stuff. Generally, not always, but that's the kind of vague idea of what goes wrong.
Yeah, I suspect the same, but I don't know if it might be interesting somehow having. I mean, the kind of theory is the easiest theory. The kind of things that is Helling is not that it has already ghost instability, so there are already problems. But it was just a proxy for something larger. But if you
so in this paper where we did that, Helling's not is one of the appendices, and it has the same problem. Yeah.
Okay. Precisely. Thanks.
So-
Okay,
This one.
great. Guys, we have time for a final question. We have 1 minute left. If someone has doubt, it's now or never. No, never now. It's you can contact Andrew later if you want. But if not, thank you so much, Andrew. It was very interesting, and we hope to see you soon. And I propose a round of applause for Andrew for his talk. Thank you so much.
Yeah, thanks for the invitation. This is very kind. It's nice to see some faces.
Great.
Okay, so thank you, Andrew. Thank you, everyone. Take care. See you soon.
Take care.
Bye-bye.
Bye bye, guys. Ciao.